but it's probably one of the most practical applications of trigonometry, and we call this solving triangles. Now I know I've really emphasized using all angles with radians, and mathematically that's still the best way to handle it, so you don't end up with using the chain rule for derivatives and things like that when you don't need to. With these solving triangles, you're almost always going to get angles measured in degrees, and so we're going to do everything here in degrees. So I would, at this point, until we get into related rate questions, which will be the next segment, probably Friday, bring your calculators on Wednesday and do your homework with the calculator. There's one thing that we aren't talking about in Math 14, which are inverse trigonometric functions, arcsine, arccosine, arctangent, but we're going to use those functions here in a very simple way to find out some angles, because we'll end up with knowing something like, what is it? Okay, we're going to end up with expressions like the sine of A equals 0.5, you know, and then we'll be able to get A from your calculator by taking the arcsine. Okay, so first a couple conventions here. Number one is we're going to be drawing these triangles, and don't attempt to draw the triangles in scale or in proportion, or even if they're obtuse and acute triangles, just draw a generic triangle, just to label it so you can visualize where you're going. You can redraw it if you want at the end to make it a little bit more proportional, but it's not necessary. What we're going to try and do here is we're going to see if we know from a minimum number of angles and sides and figure out what the other sides are. So the first thing we're going to do is decide on a convention. Okay, so we have some sides and some angles, and we want to get the rest of the angles and the sides. Now you already know how to do this with right triangles, right? If you know the two sides, you know how to find the hypotenuse. If you have the hypotenuse on the side, you know how to find the other side. We're going to do this now for general triangles. So the thing that I want to do is we're going to use capital letters for angles. So we don't have to say angle A when we mean side A and things like that. And we're going to use the lowercase letters as the length of the sides. And look where I put the sides in relation to the angle. The side A is between angle C and B, and it's opposite of A. And side B is opposite of B, and side C is opposite of angle C. Okay, so if you want to entirely draw it exactly this way, it'll work for you every time. Okay, if you want to put the B on the top and the C on the right side, that's fine and all that kind of stuff. But you know, just basically settle on a way to draw a triangle, just so you have some references to do you have an included angle or an outside angle, all this kind of stuff. And don't worry about the proportions. Just draw this triangle and everything will work. All right, so we're going to use three basic tools for this. And I'm going to spend a little bit of time, not much, but a little bit of time deriving these rules. But I prefer you just remember the rules and don't worry about how to derive them so much. But anyway, I think it's important that you see that they are justified. So one of them you know very well already. The sum of the angles in a triangle is 180 degrees. So what this tells you, if you know two of the angles, you know what the third angle is, right? You just add them together and subtract it from 180 and you get that third angle. Triangles always equal 180 degrees. The next one is what's called the law of sines. And here's where labeling your triangle is really important. When you have that side A opposite of angle A, you have this rule here that says all these things stay in proportion. The sine of A divided by A equals the sine of B divided by B, which equals the sine of C divided by side C. Okay? So this one is really easy to remember. It's the law of sines, and so you put the angles all on one part, and then the sides on the other. And incidentally, before I go to the law of cosines, you'll see this thing written in its reciprocal form as well. A over the sine of A equals B over the sine of B equals side C over the sine of C, and that's perfectly fine. And sometimes it's a little bit more useful to write it that way because you're going to be solving for one of them, and rather than dealing with reciprocals, just write it right away, either in this form or in the reciprocal form. Okay, and then we have this law of cosines, and this one is the one that tends to be a little bit more complicated. What this says is that c squared equals a squared plus b squared, kind of like the Pythagorean theorem, but we're going to subtract 2 times a times b times the cosine of c. All right. Two things are important here. Number one is compute this whole thing at once. We don't take a squared plus b squared minus 2ab and then multiply it by the cosine of c. That's not the way to do it. You're going to take 2 times a times b times the cosine of c and then subtract that quantity from a squared plus b squared. Okay, so order of operations is exactly what it says here. Don't mess it up because it's easier to subtract 2ab from a squared plus b squared before you take the cosine of c. That's not the way it works. Okay, this is one entity here, and you calculate this whole thing before you subtract it.
And it doesn't involve the big A.
It's only capital C. Okay, so this means that we know this side B, we know this side A, and we know this angle C, and so this formula tells you now you know the length of C. Okay, doesn't tell you anything about angles A and B, and you don't need to know them. Sometimes you'll know them, sometimes that's the next thing you want to find out. Okay? Now the other thing is, this looks so much like the Pythagorean theorem. What if we had C as a right angle, right? So if the cosine, if C was a right angle, 90 degrees, then we know that the side C would be a squared plus b squared equals c squared. So if the cosine of 90 is 0, this whole term drops out, and so this thing gracefully goes into the Pythagorean theorem. So it's very, very consistent with what you already know. This is just for a general triangle, not just right triangles then. Now, the other thing is that this is all of these things are symmetric. There's nothing special about A, B, or C, and in fact, the labeling is purely arbitrary on our part, so long as we keep the side label opposite the angle label. So, you know, angle B is opposite side B. So you can rewrite this with any two angles with the included angle. Okay, so if you want to know B squared, well, it's the other two sides squared minus 2 times those other two sides times the cosine of B. So these two, even though they look, well, they're a little bit different, they're in the same form, and it's just a symmetry thing, or the fact that we've arbitrarily labeled these labels. Okay, so it works for any side. You just have to make sure that you're using the other two sides and the angle that's opposite of the side that you're solving for. Okay, so let me go through briefly how you get to these things. You ever wonder why the sum of the angles in a triangle equals 180? Well, remember this from high school geometry. Alternate interior angles are equal, and that vertical angles are equal. Those two are equal. So if we were to draw a triangle, extend the two sides, and make a parallel line here, we know that these two angles, these two, A is A, the same reason why here alpha is alpha, and then C is an alternate interior angle to C, and so here this started out to be a straight line, so A plus B plus C equals 180. So that's just a geometric way to look at it. Okay, easy to remember. I'm not going to ask you to regurgitate this, but I would really hope that you're looking at these things as opportunities to understand a little bit behind what you're manipulating. Okay, so that one is the most straightforward. Everybody with me here? Can I turn the page? Okay, so the law of sines, where does this come from? All right, let me just take these two sides, A and B, and let's take the two angles A and B, and I'm going to drop the height of the triangle down. So this is perpendicular to this line here, which is normally side C, and it comes from there. And so if we do work out the trigonometry of this, we know that the sine of A equals h over b, right? That's just the definition of the sine of a. And so if we rearrange, multiply both sides by b, we get b times the sine of a equals h. If I do the same thing for the sine of b equals h over c, so the sine of b is going to be h over c. Okay, that's by definition. Multiply both sides by a, and so we get another expression, a sine b equals h. So if I make those two equal to each other, because h is h, I get this, and I divide both sides by b and divide both sides by a, I get the sine of a over a equals the sine of b over b. Now, remember, there was nothing special about a, b, and c. So if I just, instead of dropping this thing from that vertex where angle C is, if I do the same thing where angle B is or where the angle A is, I would get the other, I would also include C in this. So, and it also might be an interesting exercise for you to do this with an obtuse triangle to show that it still works. You know what an obtuse triangle is? That's where you have one obtuse angle. That would be a triangle like this. It still works with that. And by symmetry, then, we know that we get the law of sines. Okay, and I mentioned earlier, you sometimes see it like this, and they're both equivalent. The one you use is your choice, whichever makes the calculation that you're doing easier. Okay, so where does the law of cosines come from then? So I'm going to drop that same height down here, but then on this side C, I'm going to label from angle B to where H hits the hits side C. I'm going to call that D, okay? Now I'm going to do a whole lot of algebra around things. I'm going to say, because H is perpendicular to side C, I can say D squared plus H squared equals A squared, okay? And I can do the same thing for the other side that, or now I'm just solving for H squared. I can do the same for the other side where B squared equals H squared times C minus D squared. So that's just the Pythagorean theorem on this side of the triangle. And now I'm going to solve for H as well. And so I'm going to equate these two. And I'm going to expand this C minus D squared to C squared minus 2CD plus D squared. And so I'm going to subtract D from both sides. Notice I have a D squared here and a D squared there. So those just drop out, and I'm left with this expression. And so I'm going to rearrange it. The only thing I don't know and the only thing I'm not handling is D, right? But we know what D is. If we look at the definition of this thing, D is going to be the cosine of B equals D over H, or we can say, oops, D over A, I mean. And so we have an expression for D as A cosine B. I'm going to substitute that in my original equation up here, and I get B squared equals A squared plus C squared minus 2AC cosine B. Okay, so I can do this with the other two sides as well and come up with a symmetric equation. But these equations are derived by things you already know about. This is just a matter of putting them together. Once again, I'm not going to ask you to reconstruct this, but as you're becoming more sophisticated in math, you should at least be comfortable reading through these things and understanding that these things are legitimate. They're not just derived from some type of math you know nothing about. You know all the math that it takes to derive these three formulas. Okay, so by symmetry we have the others. Okay, So let's go through some examples. And here's where I think it gets a little bit interesting. So we need to know basically 3 values on the triangle to find the other 3, okay? But there's one exception to that. If we know the 3 angles, we know nothing about the sides, right? Because any time we propose a side, we can make other triangles that are similar triangles and come up with the same angles. So this is an exception to that rule that we need to have 3 values to find the other 3. We know nothing about the sides, so we stop here. So if we know 2 angles, we can find the 3rd angle, but we can't find any of the sides. Okay, so let's say we know 2 sides, and or let's say we know a side and 2 angles. So we know side C, and we know the 2 angles that are attached to C. Okay, we know angle A and we know angle B. Okay, so how can we figure this out? What's the best way to do this? What do you think? What you should do always is remember those 3 rules: the sum of the angles, the law of sines, and the law of cosines. Use them in that order. Okay, so remember them in that order. So the first thing is we know that the sum of the angles equals 180. So we can find C, right? What is C in this case? 100. Okay, so we know C is 100. So how do we find sides A and B now? Well, we can use the law of sines now, right? Because we know that the sine of C over the sine of C equals B over the sine of B equals A over the sine of A. So we substitute all the things that we know in here. And so you can solve for B and A just by taking 10 divided by the sine of 100 times the sine of 50 equals B. You take 10 over the sine of 100 times the sine of 30, and you get A. Okay, so we find that these other 2 sides equal 5.1 and 7.8. Now I want to talk about precision here. You should always be using the full precision on your calculator. But notice all of these things is just 30, 50, and 10. I have all integers here. Don't go, when you're giving the answer, don't give more than 1 decimal place, okay? So my calculator, of course, said more than 5.077, and it went on. But round that to 5.1 and round this to 7.8. But if we're going to use A and B in a calculation, use the full precision. Only round at the very, very end. And that's true anytime you're using numbers, calculating with numbers. Only round at the end, because you're going to start making some really big errors if you round too early, because your rounding errors will propagate and magnify themselves. Okay, so how many of you brought a calculator? I guess I should have emailed you. Okay, do we have enough to kind of go around? We can do these. You can set it up. So here's kind of the same deal. I know side B, and I know angle A, and I know angle B. How can I find angles C, A, and angle C and sides A and C? Now notice I put this up here as this little table right here. Sometimes organizing up your stuff in that format is pretty useful as well. Okay, so we get so 17. And B is going to be 23.2. Okay, so just keeping inventory, when we know 2 sides and an angle, we're making use of we get all 3 angles, okay, and we get a side. So this one, we only need to use the sum of angles and the law of sines. Okay, so let's look at another case here, where we're going to know two of the sides, but the angle. Now, only one angle. Now, what's significant here is that we're looking at this side angle side. Okay, so this is the case where you have side angle side. The angle that's included is 40. Now, we can't find the other angles directly, so the sum of the triangles, some of the angles in the triangle isn't going to help us. We don't know any of the ratios between angles and or the sine of an angle and the sides. So then our third rule is the one that we use. And so we can, since we know B and C, and we know A, we use the form of the law of cosines that involves A squared, right? We want to find A squared. So first write out the formula the way it is, make the substitutions, and now we can calculate this, okay? Does everybody see where I got that formula, that's the appropriate formula? Because I know B, I know C, and I know my angle A. And so I'll put those numbers in. And my admonition, again, I've seen it too many times where people, want to first multiply 2 times 5 times 7 and subtract it from 5 squared and 7 squared. Multiply by the cosine of 40. And so what we should get is this. Now, also remember that when you've calculated this here, this side of the law of cosines, this is A squared. This isn't A. Okay, it's A squared. So you have to take the square root of it. And lengths are always positive, so it's always going to just be the square root. Now, if it comes out negative, it won't ever come out negative, but you have an impossible situation if you get a negative number that you're supposed to take the square root of. So for any triangle that you can construct, you're going to end up with a positive number, and you get A. So now that we know A, what do we do here? What's the next thing? Okay, we can't find the other angles yet because we don't have enough. But what we'll do is we'll find then the by the law of sines, we can find the sine of B. Now, we haven't talked about arcsine yet, or inverse sine, but you have a button on your calculator that either is sine to the -1 or a sine or something of that sort. If you put that number in there, you'll find out what your angle is, 45.4. And then, now that you know two angles, you can calculate the third one just by summing the by expecting the sum to be 180. Okay, couple points in this. I know we're out of time here, but I want to make this point that you always use the smaller side with the law of cosines, all right? So I chose to calculate this 45.4 with this one because I'm not sure if this angle is obtuse or acute because of the explanation down here. But the rule of thumb is when you're using the law of sines, choose the smaller one first and see if you can't get around the rest by doing this, by subtracting the sum of the angles from 180.